Once again, you're all welcome. A little learning is a dangerous thing. Always drink deep or taste not the parent spring. And like I've always been saying, people that are hungry, and I mean mentally hungry, they live a life of zero excuses. They always strive to be at the top because the bottom is overcrowded. People that are hungry are unrelentless. People that are hungry are determined, they're focused, they're resilient. They live a life of zero excuses. What I'm going to do to demonstrate the Malmquist productivity index is I'm going to look at the data set. You see the data set I'm having on your screen. And this is just a recapitulation of what has happened. I've highlighted the yellow section for the input and output. Output has been normalized to 1. Okay. In other words, all of them are using the same, producing the same output. And so we're not going to focus too much on the output, but rather on the input. So this is an input-oriented model. Okay. And if you want to plot these data sets, it's a very simple thing. The first thing to do is to plot this data set. Now, the first 0-year data are in the blue, okay? And the frontier F0 is the one that captures the 0-year data. The frontier F1 captures all the firms, the same firms though, that are in the second year. Now you can see that the second year, the data is below the first year. So it shows that the frontier has shifted. Now, if you look at the second year data, the red frontier is not just below, but you can see that if it is below, then the inputs have been reduced compared to the first year blue frontier. So the inputs have come down. So in an input-oriented graph like this, the lower you are getting towards the origin, okay, the lower the input and hence the more efficient you are becoming. So this is the frontier, but then you can see that looking at the C1 to D1, the frontier is now getting closer to the B frontier. The red frontier is getting closer to the B frontier. But when you look at from above A to B to C, it is all parallel in nature. Okay, for A0 and then A1, for B0 and B1, for C0 and D1. It is parallel, it's parallel in nature, but then getting towards from the other section C ongoing, you can see that the frontier is no longer getting parallel. Now, this is an important trend and we'll be coming back to that, okay? So the F1 depicts the frontiers in year 1, the F0, year 0. And one of the DMUs is inefficient in this context in year 0. In year 0, one of the firms is inefficient. I'm sure you can identify that it is E0. Okay, it is E0. Now, I've already spoken about the Higgs neutrality of the frontier. That is not Higgs neutral throughout. It is in some part, but it's not throughout because it's not parallel throughout. Now, if you want to measure the efficiency score, the efficiency of a firm in year 0 relative to frontier 0 is the A0 in the bracket with the theta 0 outside. That is the input efficiency. The theta is representing the input efficiency. If it was phi, it would have been output efficiency. Okay. Now, because they are all 0, 0 as the superscript, this is an own period efficiency being measured. Okay. But when you see that the superscript one is the frontier 1, the one with the theta is 1, and then the DMU 1 is 0. Okay. So the way you read this is the efficiency of a firm A in year 0, but that efficiency is being measured in relation to the frontier 1. Okay, is related to frontier 1. Okay. And this is how you, and this, because the superscripts are different, we call it a mixed period efficiency. Please know that a mixed period efficiency is known as cross period efficiency. It's also known as the intertemporal period efficiency. Okay. So there are kind of different names you can give to this. So if you look at A naught, it's the same A naught in the bracket. So it's the same firm, but the same firm's score, efficiency score, is being measured in relation to different frontiers. So it is like you have Ronaldo, who is playing for Man United. And you have Ronaldo, you're measuring Ronaldo's efficiency relative to the Man United frontier. Okay. And then you are measuring Ronaldo's efficiency relative to Real Madrid's frontier. Of course, this one is different groups, but the groups can also refer to time periods. Okay. Or let's take Man United. You can look at Ronaldo's efficiency relative to 2021. And then you look at the same Ronaldo's efficiency relative to 2000. So different time periods, but the same Ronaldo, how is he performing within the two time periods? But Ronaldo we are talking about is Ronaldo today. So I'm talking about Ronaldo in 2022, his efficiency relative to 2022, that is the own period. And then relative to 2021, that is a cross period. Now, this can also be written in terms of distance functions. And I want you to know something here. The distance function X and Y are in the bracket. So that is referring to the DMU in year T plus I. Now I'm using I here instead of the 1. Of course, you can use T plus 1 so that it becomes clearly an adjacent time period. But the I here is indicative of the fact that it can be any number. It can be 1, it can be 2, it can be 3. So you can measure the efficiency or the distance function of a firm in 2022 relative to that same firm's frontier in 2016. So the time period may not necessarily be adjacent every single time. It can be different time. But in most of the time, in adjacent time period, that was postulated by Fair, Grosskopft, Norris, and Zahn, it is always adjacent. So the I can be 1. It's actually 1 in most papers. Now, this D is the distance function. So what this means is that we are looking at the Shepard distance function of a firm in year T plus 1, where in this case the I is a 1, relative to the frontier T. Relative to the frontier T. This is a distance function. What's the difference between the distance function and the efficiency score? Well, the distance function is the reciprocal of the efficiency score. Okay, and the efficiency score is the reciprocal of the distance function. So take note of that. We'll come back to this in the course of time, but just keep that in mind. And that is the last. So one is a reciprocal of the other. If you take the cross multiplication, you will notice that one is also the reciprocal or the inverse of the other. What we are going to do now is to learn how to formulate in the parlance of DEA. You see, DEA, the Malmquist productivity can be measured using different approaches. You can use stochastic frontier analysis to measure it, where you can deal with a number of multiple stochastic distance functions. Or you can use DEA to measure the productivity. Now, we want to use the DEA to measure the productivity. But before you learn how to measure, you got to learn how to formulate the model. Envelopment formulation, remember, that's what we're going to be doing. So we are going to formulate the own pure efficiency of a firm in year 0, okay, whose efficiency or whose distance function is being measured relative to the frontier in year 0. So they are all having a superscript of 0, 0. All right, how do you formulate that? Watch it. So you have the distance function of the firm. The firm is the X and the Y, both of which have the superscript T, okay, X and Y. Okay. And they're all having a superscript T relative to the frontier T, which is having the D to the power T. Now, this answer is the reciprocal. So the reciprocal of this is what we are looking for. That's why you have to the power negative 1. To the power negative 1 is simply 1 over the value, the distance function value. So what this one is saying is that in order to have, and this I want to just use something to show you. In order to have this answer, okay, we should minimize the theta, which is the input-oriented efficiency score of a firm in year T relative to the frontier in year T, okay? And this is an input orientation, so the I is indicating input orientation. The minimization, so we are going to multiply the theta by this one in that time period. And we use the theta to reduce those input and output towards the origin, in the direction of the origin. That is why it's a radial measure. In the direction of the origin, but whilst coming towards the origin, it will hit the frontier somewhere. And that becomes the benchmark or the target. In the process of the minimization, we are going to identify and find out the lambda. So the lambda are the decision variables, and then we're also going to find the theta. The theta is also the decision variable. It also happens to be the objective function. Now, how do you know that we are doing everything as own period? Well, it is, now if you look at this whole formulation, it's not new. It's something we've done it in normal efficiency. The fact that the theta is multiplying the x, the input, means that we are dealing with input orientation, because the y has no theta multiplying it. Okay, so we are not dealing with output orientation, this is input orientation. Secondly, you will see that the x and the y's are the ones that are having the t's. See, everything else is not having the superscript t. So the time periods are in relation to the input and the output. Now, the fact that you have this on the right-hand side, you have this t plus 1, okay? The fact that you have this t plus 1 on the right-hand side and t plus 1 here, sorry, t on the right-hand side and another t on the right-hand side shows that, okay, the firm in question is in year T. Okay, it's in year T. Now, the one on the left-hand side shows that the frontier in question is year T frontier. So the left-hand side is depicting where the frontier is located. Okay, well, which frontier is being used? The right-hand side is depicting the location of the firm, okay, which year the firm is. Okay, and so you can see that with a T on top here, it means that the firm is in year T. And with a T up here, it means that on the left-hand side, it means that the frontier is in year T. I have also added a convexity constraint, okay, what we normally call the non-negativity constraint, to indicate that this can be a VRS formulation. So if it is a VRS formulation, you add a convexity constraint. If there was no VRS, it means that it is CRS, and so that constraint is not come. Okay. And then finally, the non-negativity constraint, which is for the intensity factor, the lambda. So the lambda, okay, the lambda, I think this command is wrong. It's supposed to be greater or equal to 0. So that lambda greater or equal to 0 means non-negativity constraint, and the number of firms are from 1 to n. Okay. My interest basically is for you to understand the T, and where they are located, because that would determine the firm in question or the frontier in question. If you don't get it, you might raise your hand and I'll just go right. Other than that, I want you to do me a favor by formulating the dt plus 1. Okay? So I want you to formulate the distance function of a firm in year 2. As you can see, year 2 for t plus 1. The firm in year 2, but relative to the frontier in year 2 as well. So that's also own period of efficiency or O period distance function in year 2. How would you have formulated that? It's simple. What would you have done to indicate the difference? Again, it's simple. How would you show that it's simple? Well, again, it's simple. But how do you prove that it's simple? Well, it's simple. How do you do that? What you do is that the firm in question is now in year t plus 1. So this is going to be t plus 1. The firm in question is going to be t plus 1. So this in question is going to be t plus 1. Okay. So the inputs and output are in t plus 1. And then the frontier in question is also going to be t plus 1. Okay. The frontier in question is going to be t plus 1. Remember, the lambdas are not giving t plus 1. The lambdas are not giving t plus 1. So with that, what is up here will also change. Okay, they will all be t plus 1, t plus 1, t plus 1. There will also be t plus 1 here, t plus 1, t plus 1. All indicating that we are in the year t plus 1, just as this is exhibiting. So it's not difficult there. There's no problem. Of course, the last one here is the convexity constraint, and then finally the non-negativity constraint. There is no problem there. If you check this thing very carefully, there's no confusion there. There might be slight confusion when you're doing the cross period. Anyway, this is the answer I just showed you. So if you go and do the formulation very well, you're going to realize that everything is in t plus 1, t plus 1. Again, it's also own period, because you're looking at a firm in year 2 relative to the whose distance function is being measured relative to the frontier in year 2. Now, let us go and use the data set. Okay. So if we were to use this data set to do this formulation, how would you have done it? Okay. Let's use the data set to make some sense. Let's formulate the own period efficiency or the inverse of the distance function for DMUE, in year 0. Okay. So DMUE. So if you look at this data set, okay, we are going to do it for DMUE, and we are going to do it in year 0. So this is the one we are looking at here. DMUE in year 0. So we are going to measure the efficiency of DMUE in year 0, but relative to the frontier what? The year 1 frontier, the same year 0 frontier. That's why it's called own period. So how do you do that? Well, it's very simple. But how do you do it? Well, again, it's very simple, because what you want to do is to just remember the general formulation. This is a general formulation here. Okay. So the general formulation here means that you are going to write the distance function. So we'll be right at this stage, we ignore the d. Okay. At this stage, and I normally want to write it in a way that if you should have it, you will also be able to know exactly how to document that. So you will write it as d, that's a distance function of DMU E in year 0. Okay. And then this d is in year 0. So you can just use 0 there. And it is in this format, okay, x in year 0, okay, and then y in year 0 to the power -1. And then you're going to minimize this theta, which is going to be in year 0, okay, or let's use the same 0 but year t, and then x t, and then y t. So that's the first part. The frontier means that this one is the weighted sum of all the inputs in year 0. The weighted sum of all the inputs in year 0. So let's go to the input in year 0. All the inputs in year 0 are what you are seeing here. Okay, at the x1. Okay, you're seeing them at the x1 there. There's that. At the x1. So we are going to do the weighted sum of the input. What are the inputs? 3, 3, 5, 8, 7.5. And then the other inputs are 5, 5, 2, 2, 3. So we are going to do a weighted sum. Now the weighted sum means that we need to do 3 lambda A0 plus 3 lambda B0 plus 5 lambda C0 plus 8 lambda D0 plus 7.5 lambda E0. They are going to be on the left-hand side. Then for the input X1, then the constraint for the input X2 on the left-hand side is going to be 5 lambda A0 plus 3 lambda A0 plus 2 lambda A0 plus 2 lambda A0 plus 3 lambda A0. Then you do for the output. Okay, that will be 1 lambda A0, 1 lambda B0, 1 lambda C0, 1 lambda E0, and all of that. Okay. So they are going to be on the left-hand side. But the right-hand side is going to be for just the DMU whose efficiency you are assessing. And which DMU is that? It is E. So on the right-hand side, as you know in the envelopment formulation, you are going to have 7.5 multiply, and because it's an input orientation, that will be multiplying what? Theta. And then for the second constraint, it's going to be 3, also multiplied by theta, because we are doing input orientation. Then on the right-hand side, it's going to be 1, not multiplied by any theta, because we are not doing output orientation. Okay. I hope you understand what I just did. So let me just go and show you how this thing is supposed to look like. Okay. So you can see here, okay, you can see that we've written the same thing, 3 lambda A0, 3 lambda B0. All of them are going to be on the left-hand side, less than or equal to the DMU under evaluation, which in this case was E. And the contents of E were 7.5 and 3. They will have the lambda. So they will have the theta, multiplying them to indicate that we are doing an input orientation. And then you have the output constraint. The output constraint says that the weighted sum of the output should be greater than, not less than, but greater than the output of the fan we are considering. So that value of 1 that you see here, it is for the one for DMU E0. So you're taking year one. So how do you read this? You're measuring the efficiency of a firm in year 0 relative to the entire frontier in year 0. And then you have your last constraint, last but one constraint, which is a VRS constraint, the convexity constraint. And then the non-negativity constraint will be the last ones here. That is, the weight should be positive or 0 for each one of them. So this is how you do the formulation for each one of this. Okay. So normally I like you to put this in your thesis because it helps you to know that behind the scenes nitty-gritties of what's really happening in the estimation process. Now, this is on period, okay, for the firm in year 0, okay, E in year 0. But what about if we're to do the same on period, but that same firm in year T plus 1, in year T plus 1? How do you have done it? Okay, I want somebody to walk me through. So I'm showing you the previous one. Then you can now use this previous one to walk me through.
Okay, Doc. So we'll have D is 0 raised to the power T.
Now remember, you are doing it for a firm in year 1, not year 0.
Yes. So it will be T plus 1 into brackets X T plus 1 Y T plus 1.
No, start with a D. Say D what?
Yes, D is E1.
Aha. You
D
said
E1.
E0, so I wanted it to
yes, sorry. DE1 raised to the power T plus 1 into brackets XT plus 1 YT plus 1. Then we close the brackets minus 1, exponent minus 1. Yes. Minimize theta T plus 1 XT plus 1 YT plus 1, all in brackets. Subject to. Then we'll have, Doc, please, can you go to the
data?
The data. So yeah, we'll have 2.1 lambda A1 plus 2.1 lambda B1 plus 3.5 lambda C1 plus 5.6 lambda D1 plus 2.1 lambda E1, which is less than or equal to 2.1 theta.
Right.
Yes. since we are working for the firm E, the DMU E1, then we will have for the inputs 2, we have 3.5 lambda A1 plus 2.1 lambda B1 plus 1.4 lambda C1 plus 1.4 lambda D1 plus 2.1 lambda E1, which is less than or equal to 2.1 theta.
Okay.
Then when we will have the inputs, the outputs, which is normalized by 1 lambda A1, 1 lambda B1, 1 lambda C1, 1 lambda D1, 1 lambda E1, which is greater than or equal to 1. Then
add the non-negative convexity.
Yes, so the convexity will be lambda A1 plus lambda B1 plus lambda C1 plus lambda D1 plus lambda E1, which is equal to 1.
Okay. And then your non-negativity constraint. Then your non-negativity. Very good, very good. I like the way you've made justice to the work. In fact, exactly what he said is down here. Everything you said is perfectly orchestrated and beautifully organized right here. So you entered into my cerebellum and then created the formula and then moved it from my cerebellum and moved it to the medulla oblongata. Very good, well done. Okay, you can drink some water. So that is how you do the formulation. These are all own period efficiency, which is the reciprocal of the distance function. So there is no problem with that. Now, how do you formulate the cross period efficiency? Now, the cross period efficiency, which I also call the mixed period efficiency, you are rather estimating the efficiency of a firm in year 0, but relative to frontier 1. So it's against frontier 1. It's not in relation to any other frontier, but in relation to frontier 1. How do you handle that? Okay, so this is how it is. If you look at that, the firm is in year 1. That is why you have x to the power t, y to the power t. But the d, which is the frontier, the distance, is to the power t plus 1. Okay, and that goes all the way in the objective function. In the constraint, the subject to, you will notice that the left-hand side, the front is represented the frontier, the technology set. Okay, of course, it is the entire production possibility set, a polyhedral convex set that we are showing here. But that is t plus 1. So you can see that the x and the y are to the power t plus 1, which is showing that now we are measuring the efficiency of a firm in year 1, but relative to the frontier t plus 1. So that is why the left-hand side of the frontier is exhibiting t plus 1, but the firm is in year 1. So I told you that the right-hand side always shows the firm. So you can see that the xi naught, which is the DMU at the valuation, and the YR naught, which is also the DMU and the input output, the two of them are depicting the input output correspondences. Okay, the one that you are targeting to estimate. You can see that both of them are to the power t because we are measuring the efficiency of a firm in year t in relation to the frontier. The frontier is the left-hand side. And then once again, because it's an input orientation, theta is multiplying the x and not the y. So that is how you would have actually executed this one. And then look at the opposite. Okay, I'm just going to look at both of them. The opposite is that this time the t plus 1 is going to move to the right-hand side, and then the superscript t will move to the left-hand side for a firm in year 1 relative to frontier 0. Okay, instead of a firm in year 0 relative to frontier 1. So you can see the difference in that. So Who can now formulate one for me if I were to use the original data? Okay. So let's go to the original data. Who can formulate the second one rather for me? You're going to formulate the efficiency of a firm in year 2. This time you're doing it for E in year 1 relative to the frontier 0. E in year 1, but the frontier was constructed by the firms in year 0. T in year 1 relative to the frontier in year 0. Who can walk us through that using these numbers? Who can walk us through that using the numbers? Okay, who can walk us through that? Steven, can you do that?
Yes, Doc.
Okay, so walk us through that. If you want me to go back for you to see, this is the general formulation.
Okay, Doc. So what we are doing now is the cross period estimation. So we are looking at E, that's the DMU in question. We are looking at it in year 1, and we are looking at the frontier in year 0. So in formulating it, we will say D is 0. D is 0.
No, the DMU is in year 1.
Doc, please come again.
The DMU is in year 1.
Yeah, the DMU is in year 1. Okay. Okay. And the frontier is in year 0.
Yes.
Yes. Okay. So the D here we have at the beginning of the formulation, the objective function.
So it will be DE1, not the E0.
Yes. Yes. Yes, Doc. So we have DE1 to the power T plus 1 into brackets X0 XT, X to the power T, comma, Y to the power T.
Now, whatever is here will still not change. It will still
okay.
This was a but it will still be XT plus 1, YT plus
1. Okay.
To the power negative 1.
To the power negative 1. Okay, so okay, please, Doc, I want to
share something with you. The only thing that is going to change in these things are just the subscripts.
Okay.
Just the subscript, E1 here, and then E1 there. That's it.
Oh, okay.
They will remain as it is, but it is here that the real computation starts. So, can I take you back to the data to walk us through this?
Okay, okay, Doc.
So check it carefully before we go there.
Okay, Doc, we are seeing that the DMU is in year 1 and the frontier is in year 0. Okay.
Correct. The DMU is in year 1, the frontier is in year 0. Should I go back there?
Yes, Doc.
Okay. So walk us through that.
Okay, so Doc, what we have here now, we are doing the constraint for X1. So what we have is lambda 3 plus lambda 3.
No, we do 3 lambdas.
Okay, okay, sorry. 3 lambda plus 3 lambda.
3
plus
lambda
5.
what? You have to tell us.
Okay, 3 lambda is 0, sorry. 3 lambda is 0 plus 3 lambda B0 plus 5 lambda C0 plus 8 lambda D0 plus 7.5 lambda E0 less than or equal to 2.1 theta.
Excellent, excellent, excellent. Now you know what you're doing. Continue.
Then we go to the second constraint, which is also an input variable. So we have 5 lambda A0, 3 lambda B0, 2 lambda C0, 2 lambda D0, E 3 lambda E0, that's the last one. Less or equal to 2.1 theta. Then we go to the last variable, which is the output variable, which is normalized to
There's
1.
no need to go through that. It's easy.
Okay.
To 1. But that is well done. That is tricky. But that's, see, guys, the only reason why I'm letting you go through this with me here right now is because I want you to understand here right now how these things work. Once you can get it here in your own spare time, you can get it there. So I deliberately do that. It's a powerful learning process if I let you go through that. Okay.
Thank you, Doc.
That is how go through. So what you said, I gave you the one down here. That's exactly what you said. The one up was the own period for the current year, and then the one down here is the own period, is a cross period for the current year, and the one down here is a mixed period for the next year. So that's the one you just did. And I know that the VRS constraint and the non-negativity constraint are automatic if you have them. So learn how to do these formulations. These are 4 different distance functions. These are 4 different efficiency scores. And you need to know and learn how to formulate each one of them. If you can do that, you're on course. Now, let me just give a bit of cautionary note when you are estimating the Malmquist. Okay? It's something we've already mentioned. Even though their own period, and when I say their own period, I'm talking about the ones with the TTT or the ones with the T+1, T+1, T+1. Even though their own period efficiency scores or the distance functions. And in an output orientation, please note, distance function, not efficiency scores, but this time distance function. Even though this distance function, own period distance functions, are greater than 1, input oriented. And this one too will also be greater than 1 or equal to 1, even though they can be greater than 1, own period, because that firm must be feasible in that respective year's technology. So the one with the TTT must be feasible in period T technology. And the one with T+1, T+1 must also be feasible in the T+1 technology. Even though they can be greater than 1 or equal to 1. If they are equal to 1, of course, it means the firm is efficient. If it's greater than 1, it means the firm is inefficient. Even though that can happen, the cross-period efficiency scores, these ones, okay, where you have a firm in year T relative to the frontier T+1, or you have a firm in year T+1 relative to frontier T, they can be less than 1, greater than 1, or equal to 1, because they may not be feasible in that period's technology, whether it's period T or period T+1. They may not be feasible. Some of them will be outside the frontier, okay, which will make them what? Which will make them super efficient. Those who will be outside the frontier will be super efficient. And among these super efficient ones will be infeasible ones. Okay? They will generate linear programming, mixed period infeasibilities. So you want to take note of that so that when you see that in the software, you will appreciate that. So Fair, Grosskopft, Lengren, and Roos in 1992 developed a 2-part decomposition. Fair, Grosskopft, Norris and Zahn developed the 3-part decomposition. The Malmquist is an index that measures periods T and T+1, okay, distance functions, and is the geometric mean of those distance functions. And of course, the distance functions are the reciprocals or inverse of the efficiency scores. We are now ready to estimate the Malmquist productivity change index. The Malmquist productivity change index. How do you go about it? Well, this is it. Focus here. When we talk about a Malmquist productivity change index, we are talking about, actually, we are talking about 4 different distance functions. But the first one, okay, are input distance functions representing the efficiency change measured relative to frontier T. Okay, frontier T. That's the first one. It is something over something. Then the second part is the same efficiency change of the same firm measured in relation to frontier T plus 1. So you're multiplying these. But in order to avoid an arbitrary choice of a reference technology, okay, what the Fair et al. Did was to use the geometric mean. So you now take those 4 scores and then raise it to the power half, or you take the geo mean of it. And that becomes the Malmquist productivity change index. This is what we are talking about. So you can see that the first part, and I want you to know that, because if you understand this thing, you can expand the model like previous years have done. You can appreciate why they expanded the model. So these firms are being measured relative to period T. Okay, that's the first one. That's efficiency change in relation to frontier T. And then this one is the second one is efficiency change in relation to frontier T plus 1. So you can see this is what makes up the Malmquist productivity change index. Of course, we are doing it in an input-oriented version. All right. Now, the question is, if you are able to get these different individual distance functions, and again, note that they were all estimated relative to your constant returns to scale technology. That is why you see the subscript. Okay, so the subscript C means that these distance functions have been measured in relation to a CRS technology. A CRS technology. All right. Now, when you go to the next thing, is how you interpret the score. How do you interpret this Malmquist productivity change index? Well, that is sometimes dependent on whether you are using the distance function or using the efficiency scores, and whether you are dealing with input orientation or output orientation. Now, in our case, we are dealing with distance function, and we are dealing with input orientation. Now, given that definition, whenever the Malmquist is greater than 1, what it means is that the second year's input are further away from the efficient boundary than the first year's input. And in that case, what it means is that we have a deterioration in productivity between the year, from year T to year T plus 1. So in an input orientation distance function, when MPI is greater than 1, we have a decline in productivity. But that again depends on the software you are using, okay? Because when you take the reciprocal of that answer, MPI greater than 1, when you take the reciprocal of that final answer, that will mean that the MPI greater than 1 will imply progress. Okay. Now, I just said that MPI greater than 1 is a regress. Now I say when you take the reciprocal of the answer, it depends on what software I'm using, or what I'm using hand computation. And we are going to use hand computation. So with a hand computation, that answer you get, you take the reciprocal. And if you take the reciprocal, whatever answer you get, and you take the reciprocal, MPI greater than 1 is progress. It's an improvement. But if you are using the benchmarking software or max DEA software, it will automatically greater than 1 straight away. So MPI greater than 1 will mean progress. So if you have 2.2, that will mean progress straight away. But if you are using the FEAR package, okay, when you have MPI, which is 2.2, that is not progress, okay? But rather when you have MPI like 0.6, that is rather progress. So with a FEAR, okay, frontier efficiency analysis for R by Wilson, you will notice that one you need to take. Of course, in R, you can just command and do 1 over the answer, and all the scores will give you greater than 1 for the meaningful, sensible way of interpreting the Malmquist. So that way, greater than 1 becomes progress, less than 1 becomes regress. I will do this with you every step of the way, both hand computation, and then I will also do software computation with you. All right. So remember the convex isoquants, okay? And we can calculate the Malmquist productivity score for this very convex isoquant using, of course, the Malmquist productivity formula that we have right here. But before we come into the computation of the scores, at this stage, I want to crave your indulgence to see whether you have a question or whether you have any comment. So what we are going to do next time is that we are going to estimate the component or the indices, the distance functions that make up the Malmquist index. Then we shall look at the decompositions of the Malmquist. The two-part decomposition of Fair, Grosskopft, Lengren, and Roos. The three-part decomposition of Fair, Grosskopft, Norris, and Zahn. The three-part decomposition of Ray and Delsi 97. The four-part decomposition of Wheelock and Wilson. There is also the Fair and Grosskopft 96 decomposition. There is a five-part decomposition of Fair, and there is a seven-part decomposition of Fair. See, I will not look at all of them. I will not look at the five. I will not look at the seven-part decomposition. I will mention just the five-part decomposition. I will not solve it. I'll show you the formula. I will not solve it. Okay. It looks at input and output bias. I will show you that so that in subsequent papers you can write on that. Ladies and gentlemen, that brings us to the end of the entire caboodle. It's been a pleasure having all of you.